Hi everyone. Today we're going to study exponential functions. Let us first define exponential function. The equation f of x equals b raised to x defines an exponential function for each different constant b called the base. There is a restriction that the base must be greater than 0. It means b must be positive. Also, b should not be equal to 1. The independent variable x can assume any real value. It means to say, for an exponential function, we expect a variable, which is x, as an exponent. Example 1, f of x equals 2 raised to x. In here, the base is 2 and the exponent is x. Here is a quick look of how the graph of f of x equals 2 raised to x looks like. Another example is f of x equals 1 over 2 raised to x. In this example, the base is 1/2 and again, the exponent is x. Here is a quick look on how the graph looks like. There is a note that the domain of the function is the set of all real numbers r, and this is the interval notation, negative infinity to positive infinity, and the range of f is the set of all positive real numbers, and this is the interval notation from 0 to infinity. Take note, we are using the parentheses for the 0, and 0 is not part of the solution. Let's go now to the graphs of exponential functions. Here are the respective graphs of our example a while ago. The y equals 2 raised to x and the y equals 1/2 raised to x. Let us study the properties of the graphs of exponential functions, and this is the first one. All graphs pass through the point 0, 1. This is the point 0, 1. Number 2 property, all graphs are continuous with no holes or jumps. Property number 3, the x-axis is a horizontal asymptote. Asymptote is a line that the graph is approaching but never intersect. If you notice the graph, it is approaching the x-axis, but it will never intersect the x-axis. Property number 4. If b is greater than 1, then the function b raised to x increases as x increases. This is an example of a graph with b, or the base, is greater than 1. Property number 5. If b is between 0 and 1, then the function b raised to x decreases as x increases. This is an example of a graph for property number 5. Number 6 property, the function f is 1 to 1. Hi everyone. Today, we're going to study graphing exponential function of the form f of x equals b raised to x. Here are the 4 general steps. Step 1. Create a table of points. Step 2. Plot at least 3 points from the table, including the y-intercept, which is 0, 1. Step 3. Draw a smooth curve through the points. Step 4. State the domain, that is from negative infinity to positive infinity. The range, and the range is from 0 to infinity. And the horizontal asymptote. The equation of the line is y equals 0. Let us see this example. Sketch the graph of f of x equals 0.25 raised to x. State the domain, range, and asymptote. Let us write the problem down here. Let us go now to step 1. That is to create a table of points. Here is our table. For the x values, we put 0 here and 1, 2, and 3 on the right of 0, while negative 1, negative 2, negative 3 on the left side of 0. So we have here 7 values for x. Use calculator now to find the respective value of f of x. When x is 0, f of x is 1. When x is negative 3, f of x becomes 64. When x is negative 2, f of x is 16. When x is negative 1, f of x is 4. When x is 1, f of x is 0.25. When x is 2, f of x becomes 0.06. When x is 3, f of x is 0.02. For steps 2 and 3, plot at least 3 points from the table, including the y-intercept 0, 1. Draw a smooth curve through the points. Here now is our graph. We plotted 3 points, including the 0, 1, this point negative 1, 4, and another point 1, 0.25. This is now our smooth curve. Step 4. Let us state the domain, the range, and the asymptote. The domain is from negative infinity to positive infinity. The range from 0 to positive infinity. And asymptote is that horizontal line y equals 0. This is now the final answer. Example 2. Sketch the graph of f of x equals 4 times the quantity 1/2 that is raised to x. State the domain, range, and asymptote. Let us write our function here. Then step 1. Let's create a table of points. We have this table. Let us now fill in the corresponding values. We can use calculator here. Let's begin with when x equals 0, we substitute this 0 to the x here, then we will get the value of f of x. So, the f of x when x is 0 is 4. What about when x is 1? F of x is 2. When x is 2, f of x is 1. When x is 3, f of x is 0.5. When x is negative 1, f of x is 8. When x is negative 2, f of x is 16. When x is negative 3, f of x is 32. Now step 2. We plot at least 3 points from this table, including the y-intercept 0, 4. So we choose these 3 points. Then step 3, we draw a smooth curve through the points. So we have the points negative 1, 8, the 0, 4, and the point 1, 2. And this is the smooth curve. This is the graph of the given function. Now step 4, let's take the domain, the range, and the asymptote. For the domain, what are the values for x? We can see that the domain is from negative infinity to positive infinity. Then the range. The range are the values for y. By the graph, we see that the range is from 0 to positive infinity, while the asymptote is the x-axis, and the equation is y equals 0. Properties of exponential functions. Let a and b be positives, where a is not equal to 1 and b also not equal to 1, and x and y are real numbers. The first property is about exponent laws. Here are 6 examples of our exponent laws. Property number 1, when we have a raised to x times a raised to y equals a raised to the sum of x and y. Exponent law number 2, a raised to x over a raised to y equals a raised to the difference x minus y. Law number 3, ab raised to x is equal to a raised to x times b raised to x. Law number 4, when we have a quotient and this is raised to x, this is equal to a raised to x over b raised to x. Law number 5, a raised to x and the quantity is raised to y. This is equal to a raised to the product of xy. Law number 6, a raised to 0 equals 1. Property number 2 is a raised to x equals a raised to y if and only if x equals y. There is a restriction that a is not equal to 1. Property number 3, a raised to x equals b raised to x if and only if a equals b. There is a restriction that x is not equal to 0. Let's go now to sample problems. Example 1. Simplify using laws of exponents and write answers using positive exponents only. We have 2 problems here, A, B. Letter A is 2 raised to 5x minus 1 times 2 raised to 3 minus 2x. So we have here multiplication of exponents with same base. So what we'll do is simply add the exponents. So we have 2 raised to 5x minus 1 plus the other exponent is 3 minus 2x. So we can directly remove the grouping symbol and add corresponding terms. So the 5x and the negative 2x, we will combine together. It will be 3x. The negative 1 plus 3 is positive 2. So our final answer is 2 raised to 3x plus 2. For letter B, we have division of exponents with the same base, which is e. So we will subtract the exponents. So we have e raised to 4 minus 3x, then minus the exponent of the denominator, 2 minus 5x. In the next step, we will remove the grouping symbol. In the first group, we can directly remove the grouping symbol, but for the second group, we need to change first the sign of the terms inside this grouping symbol. So we have now e raised to 4 minus 3x minus 2 plus 5x. And from here, we can combine similar terms. The 4 and the negative 2, we can combine together. It becomes 2. And the negative 3x plus 5x is positive 2x. So our final answer is e raised to 2 plus 2x. Let's go to example 2. Solve for x. We have two problems here, A, B. Let's begin with A. 4 raised to 5x plus 1 equals 16 raised to 2x minus 1. First, let us check if the bases can be made equal. We can see here in the left side the base is 4, on the right side the base is 16. And we know that this 16 can be rewritten as 4 squared. So it will be like this now. The 16 becomes 4 squared. And the power 2 here, we can multiply with our exponent outside. So the 2 times 2x becomes 4x. 2 times negative 1 becomes negative 2. On this line, we can see that the bases are now equal. And according to property number 2, a raised to x equals a raised to y if and only if x equals y. It means to say we can copy the exponents 5x plus 1 in here and equate that with the exponent of the right side, 4x minus 2. And from here, we will solve for x. The 4x on the right side, we will transpose on the left. Of course, the sign must be changed. Also, this plus 1, we will transpose on the right side. The sign will be changed. So, we have now 5x minus 4x equals the negative 2 and minus 1. To simplify further, the 5x minus 4x becomes x, and this is equal to negative 2 minus 1 is negative 3. Let's go to problem B. The quantity 2x minus 1 is raised to 5 equals negative 32. I know that this negative 32 can be written as negative 2 raised to power 5. And if I do this, I can observe that the exponent here, which is 5, and the exponent here, which is now 5, are now equal. So according to property number 3, a raised to x equals b raised to x if and only if a equals b. It means to say we can now copy the bases of the left side and the right side respectively. Thus, 2x minus 1 is now copied here, is equal to the negative 2. And from here, we're going to solve for x. The negative 1, we will transpose on the right side. It becomes plus 1. And then we will simplify further. The negative 2 plus 1 is negative 1. We will divide this equation by the coefficient of x, which is 2. So we have now 2x over 2 equals negative 1 over 2. And we will cancel the coefficient of x and the divisor 2. So only x comes down, and this is equal to negative 1 over 2. This is our final answer. Example 3. Solve for x. We have here problems A and B. Let's begin with problem A. 3 raised to x plus 1 equals 9 raised to x minus 1. We can see here that we have different bases. Here is 3, the other is 9. But this 9 we can show as 3 square. So the right side becomes 3 square, that is raised to x minus 1. We can multiply these two with the binomial x minus 1. So the exponent of the right side becomes 2x minus 2. Now we can see that we have the same basis, which is 3. We can use property number 2. So when we have same basis, we can equate the exponents. So the left side becomes x plus 1 equals the right side 2x minus 2. Let us solve now for x. This 2x we transpose to the left, the positive 1 we transpose to the right. So we have x minus 2x equals negative 2 minus 1. X minus 2x is negative x. Negative 2 minus 1 is negative 3. We multiply this equation by negative 1 so that the x will be positive. So we have x equals positive 3. This is the answer for problem A. What about problem B? 3x, that is squared, equals the square of 2x plus 5. We can see here that we have same exponents. So we can use property number 3. We say that if the exponents are the same, we can equate the bases. So we have 3x equals 2x plus 5. Let us solve now for x. This 2x we transpose to the left. So we have 3x minus 2x equals 5. Then the left side becomes x equals 5. This is the value of x. Example 4. Solve for x. We have two problems. Let's begin with A. That is 2 raised to the power 3x plus 1 equals the square root of 2. On the right side, we write again this radical into fractional exponent. So the square root of 2 becomes 2 raised to the power 1/2. In this equation, we can see that the bases are same, which is 2. So we can equate the exponents. That is property number 2. So we write now 3x plus 1 equals 1/2. Let us solve now for x. The positive 1 we transpose to the right. So we have 1/2 minus 1. And the right side becomes negative 1/2. Let us now divide this equation by the coefficient of x, which is 3. And if we do that, the 3 here cancels out. And the right side becomes negative 1 over 6. We can see here that it seems that this 3 is multiplied to the denominator 2. So we got here the 6. This is the value for x. Now problem B. 7 raised to x squared equals 7 raised to 2x plus 3. We can see now that the bases are same, which is 7. So we can equate the exponents by property number 2. We write again, we have x squared equals 2x plus 3. Let us solve now for x. The binomial here we transpose to the left side. So we have x squared minus 2x minus 3 equals 0. This is now a quadratic equation. We can solve this by any method. We can solve by factoring or we can use quadratic formula. In this video, let us solve this by factoring. So the factors of x squared minus 2x minus 3 are x minus 3 by x plus 1, then equals 0. Next step is we equate each factor into 0. So we have x minus 3 equals 0, then the x plus 1 equals 0. Let us solve for x respectively. In the first factor equation, the negative 3 we transpose to the right. So we have x equals positive 3. In the second factor equation, this positive 1 we transpose to the right. So we have x equals negative 1. So these are the values for the x, which are 3 and negative 1. Today, we're going to study reflections of the parent function f of x equals b raised to x. The function f of x equals negative b raised to x reflects the parent function f of x equals b raised to x about the x-axis. This function has a y-intercept of 0, negative 1. It has a range of from negative infinity, 0. It has a horizontal asymptote at y equals 0. It has a domain of negative infinity, positive infinity, which are unchanged from the parent function. We have an example here. There is this parent function f of x equals 2 raised to x. This graph in blue. Another function is g of x equals negative 2 raised to x. This is now the graph which is in red. This is the reflection of the parent function about the x-axis. Now, the function f of x equals b raised to negative x reflects the parent function f of x equals b raised to x about the y-axis. It has a y-intercept of 0, 1. It has a horizontal asymptote at y equals 0. It has a range of from 0, positive infinity. It has a domain of negative infinity, positive infinity, which are unchanged from the parent function. Here is the example. We have the function f of x equals 2 raised to x. This is the parent function. Now, another function h of x equals 2 raised to negative x. This is now the function and a reflection of the parent function about the y-axis. Today we're going to study natural exponential function. Let us define exponential function with base e. For a real number x, the equation f of x equals e raised to x defines the exponential function with base e. In mathematics, this letter e has a numerical value equal to 2.71828 and so on. And this function here is called natural exponential function. Let us take a quick look of the graph of this f of x equals e raised to x, but in here it is written y equals e raised to x, and they have the same meaning. Now let us learn how to graph natural exponential function. Step 1. Fill in table of values with substantial number of pairs. It means we can have the table of values that looks like this. We have two columns. The first column is for the x. We have 5 blanks here that we can write the values 2, 1, 0, -1, and -2. The second column is for the f of x, and this means we have f of 2 corresponding to the value of x, that is 2, and f of 1 corresponding to the value of x, which is 1, f of 0 corresponding to the value of x, which is 0, f of -1 corresponding to the value of x, which is -1, and f of -2 that corresponds to the value of x as -2. And then step 2, plot the points and connect them with a smooth curve. Let us have an example. Graph the function f of x equals e raised to x. Our step 1 is to fill in table of values with substantial number of pairs. So we have the x with these 5 values. We have the f of x. We have the corresponding f of 2, f of 1, f of 0, f of -1, f of -2 respectively. So given our function here as e raised to x, we will copy it here. It means to say, when we evaluate f of 2, we will have e squared. For f of 1, we will have e raised to 1. f of 0 equals e raised to 0. f of -1 equals e raised to -1, and f of -2 equals e raised to -2. Using our calculator, we will have the values e squared equals 7.39. e raised to 1 equals 2.72. e raised to 0 equals 1. e raised to -1 is 0.37. e raised to -2 equals 0.14. Let us write another column and put the ordered pairs xy. So we have 2, 7.39. Second point is 1, 2.72. Third point, the 0, 1. Fourth is -1, 0.37. Last point is negative 2, 0.14. And then step 2, let us plot the points and connect them with a smooth curve. This is now the curve. Look at our first point, 2, 7.39. It is here. The 1, 2.72 is here. The point 0.1 is here. The point negative 1, 0.37 is here. And the point negative 2, 0.14 is here. And we can see the smooth curve. And this is our final answer. Let us see here the comparison of the graph of f of x equals e raised to x, and the graph is that color blue. The graph f of x equals 2 raised to x is this graph in red, and the graph f of x equals 3 raised to x is the graph in color green. Take note that all these graphs have domain negative infinity, positive infinity. And the range is open parenthesis 0, infinity. Take note, the graph of natural exponential function follows the properties of the graph of exponential function. Let us define logarithmic function. For b greater than 1, the b is the base, and b is not equal to 0, the inverse of f of x equals b raised to x. This function is an exponential function denoted by f inverse of x equals log of x base b is the logarithmic function with base b. The general form of logarithmic function is f of x equals log of x to base b. So in here, the inverse of the exponential function is the logarithmic function, and vice versa. We read this notation as log of x to base b. Please note that x equals b raised to y is equivalent to y equals log of x to base b. This is the exponential form, and this is the logarithmic form. As an example, if we have 3 square equals 9, this is equivalent to log of 9 to base 3 equals 2. Take note, the number 3 here is the base of the exponent, and in the logarithm, the number 3 is also the base. The number 2 is the exponent, and that is the logarithm value of the logarithmic form. And this number 9 is the same number for the logarithm. Let's go now to examples. This is example 1. Change each logarithmic form to an equivalent exponential form. We have here our conversion formula. So letter A is log of 5 to base 25 equals 1/2, and letter B, log of 1000 to base 10 equals 3. So let's start with letter A. This is the equivalent exponential form. Take note, this is log of 5, so we will write here the number 5 equals, the base is 25, so we will use this base as the base of the exponent. And this 1/2 here is exactly the exponent. So we have 5 equals 25 raised to 1/2. So this is the answer for letter A. For letter B, the equivalent exponential form is 1000 equals 10 raised to 3. From the given problem, log of 1000, we're going to write this 1000 again here, and this is equal to the base 10 of the log is the same base for the exponent, and this number 3 is the exponent in here. So 1000 equals 10 raised to 3. This is our final answer. Let us have the reverse process. Change each exponential form to an equivalent logarithmic form. Again, let us write our conversion formula, and we have two problems here, A and B. This is 36 equals 6 squared, and letter B, 7 equals square root of 49. Let's begin with letter A, and this is equivalent to 2 equals log of 36 to base 6. Now, this number 2 is the exponent of our exponential form. And we write equals. We put the log of the number 36, we copy here, and the base 6 of the exponent is the same base of the logarithm. So this is our answer for letter A. Now for letter B, 7 equals the square root of 49. Let us convert the square root of 49 into rational exponent. So we have 7 equals 49 raised to 1/2. And from here, we will now write the equivalent logarithmic form. This is the equivalent logarithmic form. The 1/2 or the exponent in here will be our answer here, 1/2, then equals. We will write the log of the number 7, we will write here, and this base 49 of the exponent is the same base for the logarithm. So our final answer is 1/2 equals log of 7 to base 49. This is our final answer. Today, we're going to study characteristics of the graph of the function f of x equals log of x to the base b. In some books, you will see the topic about characteristics of the graph of the parent function f of x equals log of x to the base b. This is the graph of this function when b is greater than 1. While this is the graph of the function when b is between 0 and 1. For any positive real number x and constant b greater than 0, of course, b is not equal to 1. See the following characteristics in the graph of f of x equals log of x to the base b. First, it is a bijective function. It means it satisfies one-to-one function and onto function. The vertical asymptote is x equals 0, or we say that the y-axis is that vertical asymptote. The domain is from 0 to positive infinity. The range from negative infinity to positive infinity. The x-intercept is 1, 0. And there is a key point, that is b, 1. Remember that this b is the base of the logarithm. The y-intercept is none. We say that the graph is increasing if b is greater than 1, and this is the graph, while decreasing if b is between 0 and 1. This is the graph. Today, we're going to study graphing logarithmic function of the form f of x equals log of x to base b. Here are the 5 general steps. Step 1. Draw and label the vertical asymptote, that is x equals 0. The vertical asymptote is the y-axis itself. Step 2. Plot the x-intercept, and that is the point 1, 0. Step 3. Plot the key point, and that is the point b, 1. Note that this b here is the base of the logarithm. Step 4. Draw a smooth curve through the points. Step 5. State the domain, that is from 0 to positive infinity. The range, that is from negative infinity to positive infinity. And the vertical asymptote, that is the x equals 0. Let's see this example. Graph f of x equals log of x to base 5. State the domain, range, and asymptote. Let us first identify the behavior and key points for the graph. Since b equals 5 is greater than 1, the function is increasing. It means the left tail of the graph will approach the vertical asymptote, which is x equals 0, and the right tail will increase slowly without bound. The x-intercept is that point 1, 0. And we have the key point 5, 1 that is on the graph. Again, this 5 here comes from the base of the logarithm. We draw and label the asymptote, plot and label the points, and draw a smooth curve through the points. This is now our graph in blue. This is the graph of f of x equals log of x to base 5. This is our vertical asymptote, which is the y-axis itself. The x-intercept is here, the point 1, 0. And the key point is the 5, 1. These 2 points are on the graph. Now for the domain, we write from 0 to positive infinity. the range from negative infinity to positive infinity, and the asymptote, which is the line x equals 0, or the y-axis itself. This is the final answer. Properties of logarithmic functions. If b, capital M, capital N are positive real numbers and b is not equal to 0, and p and x are real numbers, then we have here the first four properties of logarithmic functions. Number 1, log of 1 to base b equals 0. Property number 2, log of b to base b equals 1. Number 3, log of this b raised to x to base b equals x. And this x is simply that exponent of the b. Property number 4, when we have a number b raised to log of x to the base b, this is equal to x, and this x is the number of the log. There is a condition that x is greater than 0. It means x must be positive. Let's have the 5th, 6th, 7th, and 8th properties of the logarithmic functions. Let's have number 5. The log of m to base b equals the log of n to base b if and only if capital M is equal to n. This property is used normally when we are solving equations. Property number 6. This is the log of a product mn. If we are going to take the log of the product mn to base b, this is equal to the log of m to base b plus the log of n to base b. Property number 7. This is the log of a quotient. When we have m over n and we will take the log of that to base b, this is equal to the log of capital M to base b minus the log of n to base b. Property number 8. The log of this m raised to an exponent p to base b, this is equal to the p, which is the exponent, is now put down as a factor. So this is p times the log of m to base b. Take note of this property 6, 7, 8. Because the logarithm lightens up the respective operations. Look at the product. This is equal to the sum of each factor. For number 7, the division becomes subtraction. And for number 8, the exponent or the power becomes product in here. There are types of logarithmic functions and relationships. The first is the general logarithm, where we see y equals log of x to base b. The condition is b must be greater than 0, or we say b is positive, and b is not equal to 1. Also, x must be greater than 1. The next type is common logarithm, and this is equal to y equals log of x to base 10. We say that this is common logarithm when we have a base of 10. And if we have a base of 10, we can simplify the log notation into log x. So in here, the base is not written. So every time we see a log without any base, that is understood to be base 10. And we call this common logarithm. The next type is natural logarithm, and this is y equals log of x to base e. And we can simplify the notation by writing ln of x. This ln of x means it is a logarithm with base e. There is a relationship about log of x to base b. We can simplify this by taking the quotient of log of x to base 10 over log of b to base 10, or we can write ln of x over ln of b. Take note, the log of the x will be in the numerator, and the base, which is the b, will come as the log of b in the denominator. Example 1. Evaluate the following using calculator. We have here 3 values. Let's begin with problem A. This is the log of 2.335. Using the calculator, please check that this is equal to 0.36829. Problem B. Log of -3. Using your calculator, you will find an error is coming. So we write here undefined. Because of the negative value, it becomes undefined, meaning there is no answer. Because we should remember that the domain of the log is from 0 up to positive infinity. Next value is ln, or natural log of 5.26. Using calculator, the value is 1.66013. These are the answers. Example 2. Find the value of x. We have problems A and B. Let's begin with problem A. Log of the quantity x squared plus 1 base 5 is equal to log of the quantity negative 4x minus 3 base 5. Remember that we have property number 5 that says the log of m base b is equal to the log of n base b if and only if m equals n. In this case, the log with the base are same, so we can equate the values. So we can write this like x squared plus 1 is equal to negative 4x minus 3. Then we solve for x. This negative 4x and negative 3 we transpose to the left, so we change the signs. So we have now x squared plus 4x plus 1 plus 3 equals 0. Then we combine the constants. 1 plus 3 is 4. Let us now solve for x. We can use factoring method. We can use quadratic formula. Using factoring, we have now x plus 2 times x plus 2 equals 0. We know our process. We equate each factors into 0, but they are same. So we can show that x plus 2 equals 0 and another x plus 2 equals 0. When we solve for x, the plus 2 comes to the right, so we have x equals -2. Same value will come on the other factor equation. This is the value of x for problem A. We go to problem B. Log of the quantity 3x minus 1 to the base b minus log of the quantity x plus 2 base b equals log of 2 to the base b. Remember that we have property number 7. This is the log of a quotient m over n to the base b is equal to the log of m base b minus the log of n base b. In this case, the left side value we can do quotient. So we can rewrite this as the log of 3x minus 1 over x plus 2 then to the base b is equal to the log of 2 base b. We can use now again the property number 5. That means we can equate the fraction with the value 2. So that is 3x minus 1 over x plus 2 equals 2. Let us solve now for x. We cross multiply this denominator to the right side. So we will write 3x minus 1, this is the numerator, equals 2 times this x plus 2. Now we multiply 2 to the binomial, meaning to x and to the plus 2. Let us now solve for x. This 2x we transpose to the left, the -1 we transpose to the right. So we have 3x minus 2x equals this 4, then plus 1. The left side becomes x equals the right side is now 5. This is the value of x for problem B. Let's have example 3. Find x, b, and y as indicated. So we have here 3 problems A, B, C. Letter A is log of 16 to base b equals 2. Letter B, log of 64 to base 8 equals y. Letter C, log of x to base 2 equals 3. First, let us write our conversion formula here. Our main goal now is to convert each of these problems into equivalent exponential form and solve using exponential property. Let's begin with letter A. The equivalent exponential form of letter A is b squared equals 16. The b is the base, so I write the base here, and this number 2 is the exponent, so we have b squared, and this is equal to this number 16. Now I know that this 16 is the square of 4, so I can show that b squared equals 4 squared. And then I'm going to use a property of exponential function. I remember there is property number 3 that says a raised to x equals b raised to x if and only if a equals b. I can see here that the exponents are the same. So it means I can simply copy the b down here equals 4. So I have here b equals 4, and this is my answer for letter B. It means the value of b equals 4. I will just copy this answer opposite letter A. I will go now to letter B. I will convert this into equivalent exponential form, and this is the exponential form. 8 raised to y equals 64. Again, we see the base here, the log with base 8. I copy that same base in here, and this y is the exponent that I can use here. So 8 raised to y. And this is equal to, this number 64 is now here. And I know this 64 is equal to 8 square. So I have now 8 raised to y equals 8 square. In this portion, I can see that I have same base for the left and the right sides of the equation respectively. So I remember property number 2 of exponential function, and that is a raised to x equals a raised to y if and only if x equals y. I can see that I have same base, so it means I can copy the exponents of the left side, which is y, and this is equal to the exponent of the right side, which is 2. So I have now this equation, y equals 2. And this is the value of y that I want to derive from problem B. So I'll just copy this answer opposite letter B. The y equals 2. I will go now to problem C. The log of x to base 2 equals 3, and I will find the x. I will now write the equivalent exponential form of letter C, and that is 2 cubed equals x. Again, the log with base 2, I will copy that number 2 here as the base also of the exponent. The number 3 is the exponent itself, so that is 2 raised to 3. And this is equal to this number x, and I will copy it here. I will just simplify the 2 cubed, and this will give me 8. So 8 equals x. And this equation gives me the value that I want, that x equals 8. This is my answer. I will just copy this opposite letter C. So we are now complete with our answers for A, B, and C. Let's have example 1. Simplify each of the following using logarithmic properties. Letter A, log of 1 to base 16. Letter B, log of 125 to base 5. Letter C, e raised to log of 10 to base e. Let us write the properties that we're going to use to simplify the given problems here. For letter A, the log of 1 to base 16, we're going to use property number 1. It says here, for any base, and we're going to get the log of the number 1, the answer is always 0. So this is equal to 0. I will go to problem B. The log of 125 base 5. I'm going to use the property number 3. However, I need to do something to 125. I need to show that this 125 is equal to 5 cubed. So I have now log of 5 cubed to base 5. And as per our property number 3, we can simplify this into that exponent. So the answer here is 3. For problem C, the e raised to log of 10 to base e, we're going to use property number 4. And the answer here is the value which is 10. So the answer here is 10. So these are now the final answers. Let us go to example 2. Expand using the rules of logarithm. So this is log of a fraction where the numerator is 4x cubed z squared all over the denominator is y raised to 5 to base b. So this is taking logarithm of a quotient. So what we'll do is to get the log of the numerator minus the log of the denominator. So we have now log of 4x cubed z squared, that is the numerator, to base b, then minus the log of the denominator y raised to 5 to base b. In our first log here, there is a product, and to simplify that, we need to get the sum of the log of each of the factors. So let us expand this now. So we have log of 4, the first factor, to base b, plus the log of the second factor, x cubed, to base b, then plus the log of the third factor, the z squared, to the base b, then the minus log of the denominator, the y raised to 5 to the base b. We simply copied this last part here. So we have now 4 logarithms here. We can observe that there are exponents in each of the variables for the log here, here, and here. And we can still simplify that by making this exponent to be a factor of the log. So this is equal to the log of 4 to base b remains the same. Now for this log of x cubed, the exponent 3 we will put down here. So we have 3 log of x to the base b. Then plus the power 2 comes down as a factor. So we have 2 log of z to the base b. Then minus the exponent 5 comes down as a factor. So we have 5 log of y to base b. So this is now our final answer. Let us have example 3. Write the expression in terms of a single logarithm. So we have 2 log of x to base a plus 5 log of y to base a minus log of z to base a. We can observe here that the first 2 logarithms have constant in front of them. Here is number 2 and the other is number 5. We can simplify this by putting this constant as a power of the x. So let us write the problem again into log of x squared. Number 2 becomes the exponent of x to the base a, then plus the log of y raised to 5. Now the constant 5 becomes the power of y. And this is again to base a, then minus the log of z to base a. Then let us combine the first 2 logs. Because of this positive sign, we can put them as a product. So we have now the log of the product x squared y raised to 5 to the base a. And this log of z to base a, we just simply copy here. And to simplify further, this negative sign here denotes division. So we will put the 2 logs as a quotient. So we have the log of the fraction. First is the x squared y raised to 5 as numerator divided by the z, which becomes the denominator, and this is to base a. This is now our final answer. Let us have example 4. Solve for x. So we have here log of x to base b plus the log of the binomial x plus 1 to base b equals the log of 20 to base b. So this positive sign denotes product for the x and the x plus 1. So we will combine them. So we have now the log of the product x times x plus 1 to the base b equals, the right side is still the same, the log of 20 to base b. We have property number 5 that says the log of capital M to base b is equal to the log of n to base b if and only if m equals n. It means to say, since both the left side and the right side is a logarithm to base b, we can remove the logarithm directly to both sides. So you see here, the x times the x plus 1 comes down equals the 20. And from here, we will solve for x. We will distribute this x to each term of the binomial. So x times x is x squared. X times 1 is positive x. Now, for this 20, we're going to transpose on the left side of the equal sign, and the positive 20 becomes negative 20. And this is equal to 0. From here, let us solve by factoring. And the factors of x squared plus x minus 20 are x plus 5 times x minus 4. And this is equal to 0. And then for each factor, we will equate into 0. Let's start with the x plus 5. This is equal to 0. And the x minus 4 is also equal to 0. Then let us simplify both equations. X plus 5 equals 0. We will transpose the positive 5 to the right side. So we have x equals negative 5. And the other factor, the x minus 4, we will transpose the negative 4 to the right side. We have now x equals positive 4. And these are the values of x for the given problem. Let us have example 5. Solve for x. We have e raised to 1 minus 3x equals 9.62. From property number 5, it says the log of capital M to base b equals the log of capital N to base b if and only if m equals n. In this equation, we are going to apply logarithm to both sides of the equation. But since this is a variable e, we are going to apply a log with base e. So we have log of e raised to 1 minus 3x to base e equals log of 9.62 to base e. We did put e as the base for the log because we want to use property number 3 that says the log of b raised to x to base b can be simplified into x, and this x is simply the exponent of the b. It means to say we can simplify the left hand side. We can simply put the 1 minus 3x down here, And this is now equal to the log of 9.62 to base e. I hope you still remember about the natural logarithm, that the log of x to base e is equal to the ln x. It means to say the log of e, we can change this by the ln symbol. So we have now the 1 minus 3x equals the ln of 9.62. Using our calculator, we can get the value of the ln 9.62, and this is equal to 2.26384. So let us now solve for x. This positive 1 we will transpose on the right side. Of course, the sign must be changed. So we have now the negative 3x equals 2.26384 minus 1. See here, the positive becomes negative 1. And to simplify further, we will get the difference of the two numbers here. So we have negative 3x equals 1.26384. And to make the coefficient of x equal to 1, we're going to divide the equation by the coefficient of x, which is negative 3. And if we do that, the negative 3 here will cancel out. So we have x equals the 1.26384 divided by the negative 3. And we can now simplify this into negative 0.42128. And this is the value of x that we are looking for. This is our final answer. Example 6. Solve for x. We have two problems, A and B. Let's begin with problem A. Log of the quantity 3x plus 5 equals 2. Note that there is no base here. That means this is a common logarithm. We know that when there is no base, that is by default, it is 10. Let us show the base 10. So we have log of 3x plus 5 base 10 equals 2. And from here, let us convert this to exponential form. So we write 3x plus 5 equals this base 10 with power 2. Let us solve for x. We simplify 10 squared, that will be 100. 5 is transposed to the right side. So 100 minus 5, that will be 95. Divide this equation by 3. So we have x equals 95 over 3. This is the value of x for problem A. What about problem B? Log x plus log of the quantity x minus 3 equals 1. We have our property log of a product mn base b equals log m base b plus log n base b. That means this left side here we can write as the log of a product. So we can rewrite the left side as log of x times x minus 3 equals 1. And from here we simplify the product. So we have x squared minus 3x. Notice that our log here has no base. That means this is a common logarithm. When it is a common, the base is 10. Let us show now the base 10. And from here, we convert this to exponential form. So we write x squared minus 3x equals the base 10 raised to power 1. Since this is power 1, we can simply remove this. Then let us solve for x. This constant we transpose to the left. So we have negative 10 equals the right side now becomes 0. Let us solve now for x. We can use factoring or quadratic formula. Using factoring, the factors are x plus 2 times x minus 5 equals 0. Then we equate each factor to 0. So we have x plus 2 equals 0 and x minus 5 equals 0. Solving for x, this x plus 2 equals 0 becomes x equals negative 2. This x minus 5 equals 0 becomes x equals 5. We have two values of x. When we substitute these values to our problem here, this value negative 2 is not acceptable because the value for the log can never be negative. So we only accept one value, which is the 5. Example 7. Given that log x equals 2 and log y equals negative 3, find the following. We have two problems, A and B. Let's begin with A. Log of the quantity y over x. We know that there is a log of the quotient m over n base b equals the log of m base b minus the log of n base b. So this problem here we can rewrite as the log of y minus log of x. From here we can now substitute the corresponding values. The log y is negative 3, then minus the log x is positive 2. So we combine negative 3 minus 2. The answer is negative 5. This is the answer for problem A. Let's go to problem B. Log of the quantity x cubed times y raised to 4. We have the log of the product mn base b equals the log of m base b plus the log of n base b. So this problem we can write as, then we use another property about power. The log of m raised to p base b is equal to the power p comes down times the log of m base b. So we can rewrite again this right side into 3 times the log of x plus 4 times the log of y. We now substitute the values for log x and log y respectively. For the log x, the value is 2, so we have 3 times 2 plus log y is negative 3. So we have here 4 times the negative 3. Then we simplify the product respectively. 3 times 2 is 6. 4 times negative 3 is negative 12. 6 minus 12 is negative 6. This is the answer for problem B.